just saying a few words. So thanks everyone for joining us for today. Today we're happy to have Sridip Pal from the Institute for Advanced Study telling us about universality in asymptotic bounds and their saturation in two-dimensional CFTs. Thanks so much. Go ahead, please.
Thank you very much, Nima, for the invitation and all. It's a pleasure. So today my talk will be based on these recent two papers I wrote with Bauer here, who is here as a postdoc, and then people I knew before, like Diptarko from India and Iwa from Japan. My topic is universality in asymptotic bounds and their saturation in 2D CFT. So, so, so to begin with, as we all know, that we want the basic motivation here is to capture the universal features of high energy data in from CFT side. So most of the time, this data can be buried in various quantities like torus partition function or 4-point sphere correlator or 2-point torus correlator or so on. And there will be some tunable parameter, like for example, in the torus partition function, we have the parameter beta. And then the idea is by tuning this parameter to its appropriate limit, we can extract the high energy data of CFTs. And by high energy data, I mean density of states at high energy, or like behavior of OP coefficients for heavy light heavy or heavy light heavy prime, this kind of OP coefficients in the high energy limit. And most of these techniques are based on crossing kernels, which relates the various channels. So the idea is in this tunable parameter, one can write down some expansion. In high energy data, in one channel of this expansion is dominated by the vacuum contribution in the dual channel. So let us be more concrete about this. So we can warm us up by considering a 4-point function of identical scalars in 0 plus 1-dimensional CFT. So let us consider this thing, 4 identical scalars, and let us write it down in the S channel using the scaling block. So this is the most simplified version. So we can write it down as some expansion in Z. So this is a valid expansion in Z going to 0 limit. And we can see in the Z going to 1 limit, this of course diverges. And this divergence is captured by the T channel expansion. So in the T channel, we basically take this second operator and third operator and collide them. And in this Z going to 1 limit, we see the correlator is captured by this kind of divergence. And this kind of divergence immediately tells us the growth of this A delta, these coefficients. So we see these coefficients grow like a power law with some appropriate powers, which is related to this 2 delta phi, and there is a coefficient which is also precise. And this result is valid only in delta going to infinity limit. So these are the kind of things we can do using. These are the kind of things we mean when we say we are extracting the high energy data using some crossing kernels. So we can go ahead, we can do our second known example, which is the famous Cardy formula. So we start with a modular invariant 2D CFT partition function. So again, the partition function can be written down as a sum over states with some appropriate Boltzmann factor. And using the modular invariance, you can show that in the beta going to 0 limit, this thing is dominated by the vacuum, and the vacuum contribution is given by this universal factor, where C is the central charge. And once again, from this quantity, one can do inverse Laplace and obtain the asymptotics of degeneracy, which is the growth of this quantity in the E going to infinity limit. And again, this is also related to the black hole entropy in ADS3. So this kind of quantities are useful because they, so on one side, they contain some universal information of the CFT. On other side, like by ADS CFT duality, they also contain some information of black hole physics in ADS3.
So quick question.
Yep.
Are there any assumptions here on the form of the partition function as a function of complex beta, or this is fully generic? Because you use inverse Laplace transform. So
Yeah, so right now I am saying it in a more generic version, but of course there are some subtle assumptions that goes into the calculation, and as we will go through the talk, we will see those assumptions coming in and playing a crucial role.
thank you so much.
Yeah. So another example can be some modular covariant torus two-point function. So the torus two-point function in 2D CFT again can be written down as some some cylinder correlation function, which is E O tau O0 E, and then again we have a Boltzmann factor. Again, the idea is in the beta going to zero limit, this is dominated by the vacuum in the dual channel. And once I know the expression for the vacuum in the dual channel, I can do an inverse Laplace to get the asymptotics of this quantity, which is uh, this correlator of 2-point correlator of light operators in the heavy state E. And again, this is related to the eigenstate thermalization hypothesis in large central charge. So Nima and his friends worked on this eigenstate thermalization hypothesis in CFT, in specifically in the limit where L goes to infinity and beta over L goes to zero. And here, most of our focus on slightly different limit where we have central charge going to infinity and delta over C is finite, at least in the context of whenever we are in this talk, whenever I am talking about torus two-point function, I'll be mostly focusing on this quantity otherwise mentioned. Okay, so moving on. So moving on. So here we are talking about this universality, but this universality has two different features. One is the coarse grained features, and another one is the fine grained features. So as we mentioned that most of these techniques are based on this following identity, where I have a quantity which is some CFT quantity, and then there's a Boltzmann factor, and then the idea is in the beta going to zero limit, this thing is dominated by the vacuum in the dual channel, and whatever we obtain by doing inverse Laplace is a coarse grained version of this stuff sitting here. And to be specific, we have some error terms here, and this error terms precisely controls the coarse graining and precisely controls the averaging window. So so and by fine grained features I mean the features like discreteness. So the point is the discreteness is never captured by these coarse grained features. So once I have the vacuum in the dual channel, I consider the vacuum contribution and do an inverse Laplace, I get a smooth approximation of this stuff E. And this smooth approximation always produce a continuous spectrum. So 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 naively, even if we forget about this error term, naively this answer should tell us that there is some sort of averaging is going on in in backdrop of the calculation. So our main task here is to see the tail and have some quantitative control over this averaging window.
Sorry, a quick question.
Yeah,
Let's say we put the CFT on a cylinder, so or the fear in a cylinder, so that E spectrum, the sum, is discrete.
yeah.
So there is really no way to invert that and get that function, the degeneracy omega of E exactly. There's always going to be some sort of coarse graining.
Yeah, so the point is, yeah, as long as you keep finite number of terms in the dual channel, there will always be some sense of coarse graining.
Because you truncate the number of terms. Okay, thanks.
Yeah. The best you can hope is that maybe you can. So basically, you truncate and then there is an error, and then this error controls the averaging window. The best you can possibly hope that somehow put some conditions on the CFT. For example, in chaotic CFT, you expect these errors don't matter much, and then the averaging window would be very, very small. So effectively, the coarse graining is gone. But that's a very special scenario.
Okay, thanks.
Okay. So as I said, our goal is to have a refined understanding of this coarse grain approximation. So that means we will be very careful about this error piece. So we will carefully understand the tail. And so on one side, this will put the coarse grain approximation on farmer fruiting. And on other side, we will get some new quantitative results, which comes because of this refined understanding. Like we can put some bounds on the gap of the spectrum on a generic CFT. So how do we do this? So I will give initial. I will start with giving a broad overview, and then I will go into the details. So this all started with a paper which Bauer and Shasha wrote last year. So they could write down a precise inequality by carefully treating the tail. So this is the quantity they want to estimate, and this quantity, if you see this, measures the number. This counts the number of this quantity counts the number of state in this interval of width little delta and centered at capital delta. And then the idea is, as delta goes to infinity, this inequality is true, where rho zero delta is the Cardy formula, so which you naively get by doing inverse Laplace. So that's a smooth function. So this is the Cardy thing, and this is smooth. And then there are some order one corrections. And then they can show that the number of states always stays in between some order one number times Cardy growth, and also upper bounded by some order one number times Cardy growth. And these order one numbers actually depends on this weight energy with delta and like little delta. And we can also see that this inequality is only non-trivial when the lower bound is non-zero. So only when we can show the lower bound is non-zero and positive, then we can show that both the lower bound and upper bound has a positive exponential growth, and then we can immediately conclude that the whatever sits inside had a Cardy-like growth. So we need to ensure that this lower bound is positive or non-negative. And this will not happen automatically for any delta. And there is a threshold value of little delta, or half. There is a threshold value of the half width for which this phi minus becomes positive. And that threshold value immediately puts an upper bound on the gap. So the idea is, suppose you find a value of delta so that this is always positive. That means there has to be some amount of states within that width. And that means the gap in your spectra cannot be bigger than that. So that means I am putting an upper bound on the spectral gap by finding a delta which ensures that this quantity is positive.
Sorry, another question.
Yep.
Is this bound known to be, are these bounds known to be tight? Meaning that are there examples where there are theories that saturate the bound from below or above?
Yeah, so that's our ultimate aim. We want to make this inequality optimal, and by optimal I mean we would write down an inequality, and then we would find some CFTs which saturate the inequalities. So that will be our ultimate goal. So to say, answer your question, yes, there are CFTs which saturate the inequalities with appropriate values of phi minus hat and phi plus hat.
Thank you.
So in Bauer and Shasha's paper, what they found a half width which ensures the positivity of the lower bound. Hence, they wrote down an upper bound on the asymptotic gap. But their bounds seem to be not optimal, and their conjectured value was 1. And so they could not show this value is 1, but they could prove some value which is slightly above than 1. So next what happened, we could find out a function which is appropriate function which is phi minus hat, so that which actually proves the optimal gap is 1. But the way we obtained this function, it was a bit ad hoc. So we were still lacking a general understanding that how should one construct these functions phi minus and phi plus so that these inequalities are tight. And just give you an intuition, these functions phi minus and phi plus comes about because you want to control the tail of the sum and because you control the error terms. So the optimality of this phi minus phi plus is intimately related with the how you estimate the tail and how you control the errors, and then writing down a proper function which regulates those errors. So at this point, it was clear that there are two lines of development. That in one line we could try to figure out these functions in appropriate way and in a more systematic way so that we can write down an optimal inequality. And another line of development was to write down a similar inequalities for other kind of quantities. In fact, so we went ahead and we did so here the density of states is a function of delta. So we went ahead and we redid some of this analysis with making the density of states sensitive to the left and the right moving conformal weight. So it was a bunch of technical details, but at the end of the day, one can write down same sort of inequality with appropriate growth on the both sides, on the lower bound and the upper bound. And so as I was saying, so at this point, though, there were basically two open questions. So is it possible to find out the best value of this order one numbers, phi minus and phi plus, given a with little delta? And suppose we find a functional dependence of this phi minus and phi plus with little delta. Can we recover the optimal value of the width so that the lower bound becomes 0? So, 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 so at this point, we want to write down an optimal inequality here with optimal order one numbers. And we also want to make sure that this value reduces to the value of optimal gap.
Sorry,
And
uh, sorry,
yes,
sorry to interrupt. There are two questions regarding optimality. One is that whether you can put some sort of a lower and upper bounds that are saturated by some CFTs. And then
yeah,
the second one is that can you write down something that is saturated by some complex function that, because what you're doing is that you're doing some sort of, you're assuming estimate, you're starting with a function of beta as a complex function,
yeah.
and you're doing some expansions on this. So every time, yeah, so I guess you're claiming that you find examples of physical CFTs.
Yeah. So there are, yeah, so I guess I should make it clear. So as we will see later that there are two notions of optimality. One notion comes from the from a maths problem, and then it turns out the notion of optimality of the maths problem is same as the notion of the optimality from the CFT side. So at the end of the day, I could write down a CFT partition function which would saturate this inequality.
Okay, that's beautiful. Thanks.
Yeah. So that was one question where we wanted to find out the optimal value of phi minus and phi plus, and wanted to have some CFT which saturates the bound. And in another line of development, we also wanted to ask that can we write down such inequalities for more complicated quantities like OP coefficients or 2-point correlator in heavy states? Because the idea is once we can write down this kind of inequalities, then 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 we can directly borrow the results we obtain for the optimal conditions. So, so, so once we have such inequalities, one might hope to carry out the optimality analysis in the similar way. So the analysis of optimality doesn't really care about whether we are dealing with density of states or the OP coefficients, as long as we have an inequality of this sort. Is it clear?
Yes.
Okay. So now comes the math thing. We realize that this problem of optimality at the end of the day is related to an old problem, which is Beurling-Selberg extremization. So in fact this problem is you can see it is pretty old. Beurling started working on this in 1930s, And then Selberg extended his work in 1974. And, and Selberg's work happened while he was in IAS. So as I said, we will see later this optimal value of order one numbers is related to a well-known technique in analytic number theory. And 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 because here we are careful about the optimization, so we also have to be careful about whether we are including the A states or not. So as I was saying that we are basically counting the number of states in some window. So this is delta minus delta, this is delta plus delta. So here we have to be very careful whether we are including the age or not. So it turns out that we need some refinement of the original inequality that was written down by Bauer and Sasha. So we want to break it apart in two different quantities. One is where we do not include the age states. So we do not include the age. And in this case, we do include the age. And then we found that the optimal bound is related, optimal bound value of this order one numbers is 2 delta plus 1, and the lower bound is 2 delta minus 1. And again, these bounds are, so the whole point is the lower bound saturates the number of states within a window when you do not count the age states, like do not include the age, and the upper bound saturates the states when you include the age states. And that's why you can see that the lower bound and upper bound differs from each other, but still you can have saturations in both directions. And also we found these inequalities are saturated by CFTs with spectral gap of 1. And from this equation, you can also see that when twice delta becomes 1, the lower bound becomes 0. So this immediately tells you that the other thing which was already been derived by us, that the optimal spectral gap is actually 1. So if you do this analysis for all the operators, this bound is trivial because is saturated by the descendants. But then the whole point is one can make this analysis sensitive to only Virasoro primaries, and then it's a non-trivial statement that the optimal spectral gap between Virasoro primaries is 1. So that means take any 2D CFT with unitary, modular invariant, and discrete spectrum, and take any asymptotic, take any window of size 1, there will always be some state within that window. And a nice example would be monster CFT. In monster CFT, the gap is precisely 1. And that tells us that this, at least in terms of the optimal gap, this is in terms of optimal gap 1, this is the best we can achieve, because we cannot prove a bound which is less than 1, because then the monster CFT would be an counterexample. So 1 is the best we can do. So yep.
Am I understanding this correctly? That so if you want to restrict this only to say your sort primaries,
Yeah,
you're working with, you start with a partition function that only has a sum over your sort primaries, and then you inverse
right.
cross transform that and keep track of the errors.
Yeah, yeah,
Thanks.
right. So next we can also write down a fixed spin version of this. So in the fixed spin version, the key input is T invariance. We use the T invariance to show that the spins always has to be integer. And once we know in a partition function spin has to be integers, we can do a Fourier projection on the fixed spin. So basically one can write down a fixed spin partition function and play the same game. and and then we can also find another inequality with some optimal bounds. So you can see here that this optimal order one numbers changed. Earlier it was 2 delta minus 1, but now it has become 2 delta minus 2. And this is expected because again, if you take monster times monster, you will see that the optimal gap is 2, because if you want to keep spins fixed, then you have to increase the left conformal weight and the right conformal weight both by 1. So that means your scaling dimension increased by 2. So this tells you that, so this value immediately tells you that the optimal gap is 2 for the fixed spin case. So now one can generalize this to OP coefficients. So morally, we expect similar bounds and saturations once we can write down the basic inequality. So the results for these OP coefficients was kind of expected, but there are technical hurdles, because the point is, like, when we are thinking about Virasoro primaries and density of states, there was an important input that the characters for C greater than 1 CFTs are universal. And one can write down a expression of those characters in a closed form. And then one can write down a explicit partition function which only counts the Virasoro primaries. But this is not really true when you talk about OP coefficients, because then instead of characters, what you have is called conformal blocks. And then the conformal blocks are not explicitly known, unlike the characters. So we can only get handle on this by doing some numerics. So here the basic idea is that from the density of states, from this calculation of density of states, we understood that uh, the only thing that matters is this thermodynamic limit, is this limit, which is a simultaneous limit of beta going to 0 and delta going to infinity. So we only need to know these conformal blocks or characters only in this simultaneous limit. So once, either numerically or by some other means, once we have some handle on these conformal blocks in this particular limit, we can play the same game and write down the same inequalities, and then again borrow the Beurling-Selberg extremization problem and write down the same kind of inequalities. So if we do this, then here's an expression for the OP coefficient. So here we are looking at light, heavy OP coefficients, and then square. And then again, I have AJ minus and AJ plus. So these two quantities just refers to the fact whether I am counting the states appearing on the edge of the interval or not. And again, I have a similar kind of bound. So this A0 delta, this bound, this thing is the exponential growth, which is obtained by the naive Cardy-like analysis where you do inverse Laplace. And then there are a bunch of pieces which only comes because we are trying to be more careful. So here, for example, you can see that this order 1 number changes a little bit. So here the fixed spin gap is 4 instead of 2. And that comes about because we are considering identical scalars. And basically, you are fusing two identical primaries and looking at the OP channel. And because of this identical scalar, there is some extra symmetry. And then that's how the fixed spin gap becomes 4 from 2. And also, so this A0 delta has been obtained previously in literature by one of the paper written by me, Diptarko, and Shobik, and also later by Maloney, Scott, and other people. But all of us missed this 1 over h piece. So this presence of 1 over h is a new feature, where this h is the saturation value of the Generalizing recursion block in this simultaneous limit. So this recursion block appears because, as we are saying, that it's important to evaluate the conformal block in the simultaneous limit. It is not possible, like we have not been able to analytically compute this conformal block in the simultaneous limit, but one can do numerics, and by numerics one can find this value 1 over h. So only in large central charge h becomes 1, and but or if the h becomes 1 when the value of the external things, these external operators O, is near the threshold value C over 32. Otherwise, it differs from the value 1. So next we plot this saturation value of H.
Sorry,
So yeah.
few more words. You said saturation value of the Molodchikov's recursion block.
Oh,
What do you mean by
I
the
guess I should be
saturation
careful.
value of it?
Oh, yeah. So what I meant that, so you have this function h which appears in the expression for the conformal block, right? So this h can be written down as a function of q, and which is like e power minus beta, and the internal dimension h.
Yes.
And now we want to look at this simultaneous limit, which is this limit. So we want to look at this block in this particular limit. And it
Right.
turns out that, sorry, in this limit, this block saturates, this value of this block saturates to a particular number, and that number is h.
Sorry, when you say saturates, meaning that there is some, this block satisfies some inequality or something that is saturated, or?
Oh, I guess I should not. So, but okay, when I say saturate, I means this curve just flattens out. I guess
I see.
saturate is probably, yeah, it's
Thank
a misnomer. Yeah. So I just mean, so if you can see, you have here we have plotted h minus 1, which is the deviation from 1, because earlier we expected all the earlier results had h equals 1. So we plotted this how h differs from 1, and you can see that there are regimes where h actually differs quite a lot from 1. But the point is, it always gets flattened out, and this flattened out value is what we want and what appears in the expression for the asymptotics of OP coefficient.
you mentioned this, but what is eta again?
Oh, sorry. Eta is this ratio H over C.
I see. Okay, thanks.
So we are plotting against various central charge, the ratio of the external operator and the central charge. So yeah. So it turns out this deviation is very small when H over C is 1 over 32. And as we go away from this 1 over 32, uh, this H becomes different from 1, and that gives an order 1 correction in the asymptotics of the OP coefficient.
Is that 1 over 32 the first point in the diagram, or part 2?
Say that again, I didn't catch it.
Is the point 1 over 32 on this plot, or?
Yeah, this is the 1 over 32.
I see. Okay, thanks.
Okay, so yeah, and then the similar bounds can also be obtained for 2-point correlators of light operators in heavy state. And for finite central charge, this results is obtained for t over beta being finite and both of them going to 0. And here again you can see that the leading answer is the thermal 2-point function. So it effectively tells you that the 2-point function of light operator in some heavy state is related to the thermal 2-point function. And this rho 0 delta counts the number of states within this window. And then there is some order 1 correction, which comes from carefully estimating the error terms. And here you can see that this order 1 number is same as the order 1 number appearing in the density of states. So the point is this: all these features are universal across analysis of any asymptotic quantities in 2D CFT. So is it clear?
Yes, yes. Thanks.
So for the rest of the talk, I will be mostly focused. So once we have this idea that there are some general features which holds for all kinds of asymptotic quantities, for the rest of the talk, I will be focusing on density of states, and our goal would be to understand some of the techniques which we use to arrive at this inequality with some optimal number 2 delta minus 1 and optimal upper bound with 2 delta plus 1. Okay, so we are going to start with the Naive-Cardy formula at this point. So how does the Naive-Cardy formula work? So in the naive Cardy formula, we start with the 2D CFT partition function and we use modular invariance. So we write z of beta as z of 4 pi square over beta, and then we approximate it as in the vacuum from the vacuum channel. So this is pi square c over 6 beta, and plus there are some tails. So at this point, the naive argument is that each of these terms in the tails are exponentially suppressed. So in figuring out the density of states, this tail should not matter. But here we make a crucial assumption that the error remains an error under inverse Laplace transformation, which is not at all true. So the error might not remain error under inverse Laplace transformation. To see that more specifically, we can do the following thing. So formally, we can write down rho of delta as inverse Laplace transformation of this quantity, right? So we write down like this, and then I integrate it from minus I infinity to plus I infinity. Sorry, just a second, I miswrote. So this goes from minus like this, because I already have the I here. So formally, rho of delta looks like inverse Laplace transformation. And then one could naively argue that in the beta going to 0 limit, z of beta plus it is dominated by z of 4 pi square beta plus it. And then one naively replace this by the vacuum contribution, which is this thing, and do the inverse Laplace transformation and gets a Bessel function, and that gives the naive Cardy formula. But there is a serious problem with this argument in the following sense. This integral is never convergent because of the thing we know as recurrence. So if we look at this quantity z of beta plus it, so at a fixed beta, if we treat it as a function of t, there will be recurrence where it will come back to its value at t equals 0. So that means for t going to infinity, we will have multiple recurrence in this integrand. And because of this multiple recurrence, this rho of delta can never be convergent. And which makes sense because we knew that rho of delta is a bunch of Dirac delta functions supported on the physical spectrum. So this immediately tells you that we need some sort of regulation. We need to cut off this integral at some finite t and do some estimation of rho delta. And cutting off so we need to cut off the integral t. And this cutting off precisely implements the averaging. So the cutting off integral means rho delta becomes smooth via averaging. So is this argument clear why we should not trust the naive Cardy formula completely?
So just one quick
Okay.
question.
Yeah.
So this is, I understand that you expect recurrences because you are in finite volume, right?
Yeah.
Uh, but what if you are in infinite volume? Is that true that you can never really, this never converges?
Oh, wait. So even at finite volume, there are recurrences, right?
So I'm saying that in finite volume, I'm sure there are recurrences, but I'm asking what.
Oh, even at infinite volume. Okay, I see. Yeah, I guess so. The point is even at when you say infinite volume, basically you are looking at beta over L going to 0 limit, right?
So, I mean, if the spectrum of the Hamiltonian is
Yeah.
completely discrete, it's all point
Yeah.
spectrum, then of course it's going to have recurrences. But
Yeah.
the
Yeah.
spectrum of Hamiltonian has continuous pieces as well. Is it true that it's
Oh, I see. Yeah. So one of the basic, okay. So the point is, here I am assuming the spectrum is discrete, and that's why there are recurrences, right?
so you're assuming finite volume? Because that
Yeah,
implies
yeah.
that.
Because the point is here, the integral, like whenever so beta goes to zero, but the point is this integral is still is like we are still doing the integral in finite beta over L. So effectively, we are at finite volume, even if the ratio is very small. So the point is in CFT, this beta, so we have this ratio beta over L. Only this ratio matters. So infinite volume means this strictly being zero, but we are not doing this integral at strictly zero limit. So we have to do this integral at some finite value of beta over L, which is very small, and then take the limit.
I see. I see. Thanks so much.
Okay. So we can also see this in a nice picture. So this is the spectral form. So also I should mention that this z beta plus it, if you take the modular square, this is called spectral form factor, and this is a well-known quantity. People study this quantity to look at chaos, like features of chaos in spectral form factor. So here we have plotted the spectral form factor for 2D Ising model. And here you can see, here the idea is that for beta going to zero limit, when we are at at low time, at less time, when near t equals zero. So this part is dominated by the vacuum channel in the dual frame, so which is the S dual channel. And this is the quantity we want to do the inverse Laplace on. But then as we go down, there initially there is decay, which is fine, which matches with our naive notion. But then again, it jumps up and there is a partial recurrence. And then again, there is a partial recurrence. And then for Ising model, if we go a little bit further, you will see a full recurrence. So the point is, if I do the full integral from 0 to infinity along this line, we will never get some convergence. So we have to cut it off. So, so the idea is that we should cut off the integral at some point where t reaches the recurrence period. So that's the naive intuition, and we will see that uh, that we should cut off the integral t at the value of twice pi, which is the recurrence period of monster CFT.
Sorry, is there a simple way to see why these peaks are becoming? Is this true at all that the height of the peak is coming down and is becoming fatter, wider?
Oh, for Ising model, uh, you
No, I
can.
I meant in general. Is there a general argument this is true? This is generic behavior, or is it just this particular example?
Oh, I think this is a generic behavior, at least for load, like at least for when you look at the sum. So basically what happens when you increase t from zero, dephasing starts to happen on the various terms. So even if there is a recurrence, it might not be the full recurrence. So the so
Yeah.
so so the fact there is not full recurrence at this point just means that there is some dephasing happening. And for a chaotic CFT, you actually expect a completely different thing. You expect that there will be decay and there will be ramp and there will be plateau.
Okay, thanks.
Okay, good. Okay, now to estimate this. So now we want to see how we can do this estimation and how we can regularize and cut off the integral. So do this, we should look at this picture here. So basically we want to count the number of states within this window. And then we want to approximate this window by two functions, phi plus and phi minus, which goes slightly above and slightly below of this characteristics function of this window. And then we multiply these functions with some numbers here so that the inequality still holds. And then we integrate with this density of states. And then we have a basic inequality of this form. Now you can see that there is this phi minus delta prime and phi plus delta prime appearing, and this will play a crucial role in regulating the sum. So if I go to the Fourier space, then I can write down this. So if we take the upper bound, we can write down this inequality in the following form, which goes from minus lambda to lambda dt z of beta plus it, then e power it, sorry, this, and then I have phi plus or minus hat of t. So now you can clearly see. So and compare this expression with the naive expression where we had rho of delta as minus infinity to plus infinity dt z beta plus it. So in the naive expression, the t is integrated from minus infinity to plus infinity. But now here we have these functions phi plus minus hat t. So if I choose my original functions in a way so that the Fourier transform has compact support or bounded support from minus lambda to plus lambda, then I will be able to control this integral. So that means I have to choose some functions phi plus and phi minus, which upper and lower bounds are characteristics functions, and which also has the property that in the Fourier domain, they have a finite bounded support so that it can cut off this inverse Laplace transformation. So once we have this notion, then basically it boils down to evaluating this integral properly. So we do the following thing. So we have this thing z of beta plus it phi plus hat of t dt. Now we know that the asymptotics is controlled in the dual channel. So basically we go to the dual channel like this. And then the idea is to take this thing and separate out in two pieces. One is light, which have all the contribution from the states less than c over 12. And one is heavy, which has contribution from all the states delta greater than c over 12. And so basically I am keeping the full tail in this heavy contribution, and the light part only comes from here. So and then we will evaluate this integral for the light part and the heavy part separately. So we go ahead and we do the following thing. So for the light part, I can approximate it as pi square c over 6 beta plus it. And then I have to do this integral zl phi hat plus t dt. And then one can show that this light part integral is dominated by t equals 0, which is, so this integral goes from minus lambda to plus lambda. So one can show that this integral is dominated by t equals 0, and this gives you the naive Cardy formula times twice phi hat plus 0, which comes from the fact I have t equals 0, so I just plug in this value here. And then I have the heavy part. So I still need to show that the heavy part is suppressed. So to do that, we basically estimate the heavy part with its absolute value. And the absolute value goes like e power 4 pi square over beta square plus t square delta minus c over 12 with a sum. And now the point is, because this delta is greater than c over 12, this quantity is positive. So that means it's decaying. And that means this integral will be dominated by the extremal point of this integral. So it will be dominated by t of the order of lambda. And so I can evaluate this integral ZH phi plus hat T dt by using the fact that is dominated by T order of lambda. And then I will find there is some leading growth, and then all I want that this the contribution coming from the heavy state is suppressed compared to the contribution coming from the light states. And this requirement immediately tells us that lambda is less than equals 2 pi. So roughly speaking, you have light contributions and heavy contributions. Light contribution is dominated by T equals 0 and gives you a Cardy growth. And the heavy contribution is controlled by the extremum of this, the extremal point of this integral, which is T equals lambda. And then you get another growth, which is a function of capital lambda. And then you choose your capital lambda in a way so that the heavy states are suppressed, because this capital lambda is in your hand. It only depends on the support of this function phi plus minus tau plus minus t.
Sorry, I'm a little confused. So
Okay.
lambda was the cutoff that we were picking, right?
Yeah.
What does it mean that lambda is less than 2 pi, less equal to 2 pi?
Oh, so it means that I have to pick the cutoff in a way so that lambda is less than 2 pi. Only for lambda less than 2 pi, the contribution from the heavy states are suppressed
I see.
compared to the contribution coming from the light states.
I see. Self-consistency. I see.
Yeah, so the point is, if lambda is not less than 2 pi, then again the error term spoils your calculation.
Thanks.
Okay, so I have lambda less than equals 2 pi. By the way, how much time do I have?
I think, how much time do you need?
I don't know, like 15 minutes probably.
That's perfectly fine. Yeah.
Okay. Okay. So the take home message from this analysis is we want to find out two functions, phi plus phi minus, such that in Fourier domain they have a bounded support, and in particular the support has to be less than twice pi. So once we know this, then we can relate it to a completely different problem, which is called Beurling-Selberg problem. So it took us some time to actually come across this problem and realize that this problem is related to our problem. So in the Beurling-Selberg problem, the statement is following. So we forget about the CFT for now. The statement is following. You consider exactly this kind of window, which is the characteristics functions of some interval. And then you take two continuous integrable function, phi plus and phi minus, which majorize and minorize the characteristics functions, which is a technical term to say that the phi plus is bigger than this indicator function and phi minus is less than the indicator function. And then you also require that these Fourier transforms of phi plus and phi minus have finite or bounded support. So these are band limited functions. And you say that the band limit is some number, some twice pi, 4 pi, or something, some lambda. And once you fix that, then you ask these two following questions. What is the maximum value of phi hat minus 0? And what is the minimum value of phi plus hat 0? So this is the problem of Beurling and Selberg. And if you recall, our inequality was also precisely in this form where I had twice pi, phi minus hat 0, rho 0 delta, some stuff sitting here, and twice pi, phi plus hat 0, rho 0 delta. So basically there is a similarity between these problems. So for optimality for the best bound, I want to maximize this phi minus hat 0, and I want to minimize this phi plus hat 0. So Beurling and Selberg solved this problem, So we can basically go through the solution and mimic the same process in the CFT. So to solve this problem, we want to do it in 2 steps. So first we want to obtain an upper bound on the minimum and the lower bound on the maximum. So once we put an upper bound on the minimum and lower bound on the maximum, we can write down a function phi plus and phi minus, which actually achieves this bound. So we have some upper bound and we have some condition, we have some example which saturates the bound. So that means that has to be the extremizer, at least for the math problem. And once we solve the extremizer from the math problem, then comes the second question, whether we can find a CFT example which actually saturates the bound. So that's the next step. So let us first consider the math problem. So in the math problem, to put a bound on this thing, we start with a Poisson summation formula, which basically relates the phi and its Fourier transform, so which is in this form. Now the crucial point is, in both sides, to begin with, the sum runs over all the integers. But we know that in the Fourier domain, phi hat has only support within twice pi. So that means this only contributes, this whole sum boils down to this single term here. So that's a crucial simplification. So on the left hand side, I have this. And on the right hand side, I have sum over integers. And now I know this phi plus and phi minus are basically the majorizer and the minorizer of the characteristic functions. So I can use these bounds and replace this phi plus and phi minus with these theta functions. So that means I immediately get a bound on phi, on the lower bound on the phi plus hat 0, and the upper bound on the phi minus hat 0. And at this point, this r can be arbitrary, but we need to choose a particular value of r so that this gets maximized. So we can easily do that. So if you look at this thing, then you will see that it effectively boils down to a problem of accommodating integer points inside this box, inside this characteristics point. So the point is, given a value of delta, how many integer points can you fit inside this window? If you give it a little bit of thought, then you will see that r equals 0 give you the optimal situation where you have maximum number of integer points inside this window. So you can immediately write down twice pi phi plus hat 0 is greater than equals to delta plus 1, which is precisely the number of points you can fit in a window of twice delta, when twice delta is integer. So I should have mentioned earlier, so the analysis I am doing here holds for 2 delta belonging to integer. For 2 delta not being integer, it becomes more complicated. One can still do it. We have done it in our paper, but I'm not showing it right now. And in the same way, we can show that twice pi phi hat minus 0 is less than equals twice delta minus 1. And you can see there is a difference between 2 from the upper bound and lower bound. And this comes from the situation when you take out these 2 integer points from the edge. And that's precisely corresponds to this difference of 2. So now we have to construct a function which actually saturates this inequality. And then it is very much clear from this picture, how do I need to construct the function. So this function has to be constructed in a way so that it becomes precisely 1 at the integer points inside, and it is 0 outside any integer outside this interval. At any integer point, this function has to be 0. So let us do this. So as I was saying that we have this equality from the Poisson summation formula, and from that we write down these bounds, and then we want to know how these bounds are saturated. So these bounds are precisely saturated. So the first point is that this value only depends on the value of the original function evaluated at integer point, because I have said r equals 0. So I only need to care about these functions which are only evaluated at integer points. So as long as I make sure that outside the interval at integer points, this function is 0, and inside the interval at integer points, this function is 1, we are good. We know that this equality has to be satisfied. And then it turns out that we can write down an extremal function of that kind by a nice trick which was figured out by Beurling-Selberg. So the phi plus looks like this function, which has all the nice properties of being 1 inside the interval at integer points, and outside the interval at integer point this is 0. And in the same way, you can write down a phi minus, which has at the integer points this is 1, and outside the interval and including the age this is 0. And you can see there are two free parameters, lambda plus and lambda minus. You have to tune these parameters lambda plus and lambda minus in a way so that phi plus is above the indicator function and phi minus is below the indicator function. So once all the dust settles, you can once all the dust settles, you can arrive at the inequality I was writing before, that the lower bound is twice delta minus 1 rho 0 delta. So this is the lower bound, and the upper bound is twice delta plus 1 rho 0 delta. So either you can evaluate this by looking at this construction of the function, or you can take this phi plus and phi minus and explicitly do the Fourier transform and evaluate this phi plus minus at 0. So either way, we have an example of phi plus or phi minus, which precisely produces this value, which is the saturating value. So now once we have solved this math problem, like we cannot claim that this is the saturation value for the CFT, because someone might claim that this is only an artifact of our method by which we are trying to figure out the density of states. So we need to find a CFT partition function which actually saturates this bound. And it turns out there are a full zoo of saturating modular invariant partition function, which one can construct using this polynomial of J function. And J function is the modular invariant partition function for monster CFT. So once we have this, basically for central charge, for any central charge which is multiple of 4, we can construct a modular invariant partition function with integer gap. And whenever I have an integer gap, the CFT spectrum would saturate these inequalities I wrote down before. And that also comes most naturally, because if you again look at this picture, you can see that if the spectrum is supported at integer points, then at integer points, I have chosen my phi plus and phi minus in a way so that these are 0 outside the interval. So they do not matter. We do not lose anything. And inside the interval, they are precisely 1 at integer points. So we are doing an actual counting, even though we are using this phi plus and phi minus, whenever the CFT has an integer spectrum, integer gap spectra. So these are the saturations from CFT. So one can also write, yeah.
Is PFK a polynomial? What is PFK?
Oh yeah, so P of K is a kth degree polynomial of the J function, right?
And so, for example, say if I pick it to be like J tau squared, like
Yeah.
what is that CFT? So it's the J function is a partition function of monster, but what is that?
Yeah, so okay, I see. So here I guess I should mention this. So whenever I am talking about CFT, I just mean a modular invariant existence of a modular invariant partition function. So ideally I should, so it may not be a full-fledged CFT, because of course I have not imposed crossing and anything else.
I see. Thank you.
But of course, a trivial example would be monster CFT from this zoo, which we know exists as a CFT. So,
Okay.
okay, so now we understand that. So I should mention one more thing. So for 2
Sorry.
delta,
I,
when this in, yes.
Sorry, I'm still a little bit confused. Then, in what sense are there two different questions? In one case, you said one question is a math problem. The other one is like whether there actually exists an explicit CFT. But if you define the part, I mean, if you what you mean by an explicit CFT is just a modular invariant partition function.
Yeah. Oh, yeah. I can tell you one more thing. Then I guess it would be clear to you. So the point is, I just told you that the construction of extremal function for 2 delta belonging to Z, you can do a similar thing for 2 delta not belonging to Z for arbitrary integer. So the maths problem still has a solution. So maths gives you a solution, but we have not been able to construct any modular invariant partition function which matches with the math solution.
But it doesn't mean that are you saying that it's not clear whether there exists a modular invariant partition function with that, or?
Yeah. So the point, so I guess I should be more clear. So the point is, when 2 delta belongs to integers, then the thing that saturates has a integer gapped spectra. But when 2 delta doesn't belong to Z, then the math solution tells you that this spectra would not be integer gapped anymore. There it would be some complicated, it like the it would be some complicated roots of sinusoidal function, like sinusoidal Bessel functions and things like that. So now you need to construct a CFT partition function which has physical operators lying at some roots of some Bessel function or some complicated function.
Yeah, but it's not like you do know that it's impossible.
Yeah, it sounds like it's almost impossible.
I see. Okay. Okay. Thanks.
Yeah. So, but the point is, we did not have a proof that it is impossible, but it sounds like it's almost impossible to find a solution for 2 delta not belonging to Z, where the math solution matches with the CFT solution.
Thanks.
Okay, now to conclude, we have some. I want to just give you a bird's eye view, some general features which we learn from all these techniques and everything. So this will be pretty quick. So all these results fall into a general statement of this following kind, that the microcanonical ensemble with order 1 width is same as the canonical ensemble. And we know that eigenstate thermalization talks about a single eigenstate. So it requires one more step where one can make the energy with exponentially small or pick up eigenstate. So normally people claim that the asymptotic growth of the OP coefficients or asymptotic behavior of the OP coefficient says something about the eigenstate thermalization. But one of the important point here is that whatever statement we can show by using the Cardy analysis is of this kind, and it requires one more non-trivial step, which takes this order 1 width to an exponentially small width, which is still an open problem. And then the next point is, as I was emphasizing, that there is a difference in the lower bound and upper bound, which is exponentially large, because if you remember, the bound was twice delta minus 1 on the lower side, and on the upper side it was twice delta plus 1. And since both are saturated, the resolution to the puzzle is that one can potentially have exponentially large number of operators sitting at the endpoint of the interval. So this is true for rational CFTs. We can indeed have accumulation of primaries at some particular point, but we don't expect such behavior for chaotic CFTs with non-degenerate spectra. So we expect for for chaotic CFT, somehow one would be able to write down an inequality of this form, where you can see that order 1 number becomes an exponentially suppressed number here. But again, it's not clear exactly what conditions should we put on the chaotic CFTs or the CFTs so that one can write down such inequalities. And then there are other general features. As I was mentioning before, the leading answer always comes from the vacuum in the dual channel, and the tail controls the size of the averaging window. The size is order 1 and optimal considering all the CFTs, and the rational CFTs come close to saturation. So for chaotic CFT, we expect that the size would be exponentially small, but presumably for the chaotic CFTs, one can better estimate the tail. So some extra condition has to go into this analysis, but still it is not clear what kind of extra conditions we want for this to happen. And then if we move on and look at the large central charge analysis, then we have a universal Cardy-like formula only for delta greater than C over 6, not for delta greater than C over 12. And the optimal bounds in this regime has not been found yet in the C going to infinity limit. The optimal bounds can only be recovered in a double limit, where I take the large central charge limit and followed by a large scaling dimension limit. So we do not still have a generic picture of optimality as a function of scaling dimension over central charge. So if I consider delta over C being finite and C going to infinity limit, ideally one would expect that there will be some bound which is a function of delta over C, and there will be some notion of optimality. But this notion of optimality in this limit has not been cleared yet. But what we can still show that this up bound stays order 1. It does not become exponentially small. So that problem is, so even if you expect that C going to infinity limit would be chaotic, we are not able to pinpoint that it would become exponentially small. The bound is still order 1. And then another comment is the Hawking pace transition happens at beta equals 2 pi, as we all know. But then this has two different effects in terms of the microcanonical ensemble. So, and that comes from this thermodynamic relation, how beta is related to delta. So in the normal Cardy-like analysis, beta is related to pi square root C over 3 delta, where here beta is related to C over this quantity, which is delta minus C over 12. And then you can naively argue that the beta less than twice pi is the thermal regime, and this precisely tells you that the thermal regime has to correspond to delta greater than C over 6. So basically so here it is important because naively we expect that the BTZ threshold is delta equals C over 12. So BTZ black hole starts to exist after this, but only after delta greater than C over 6, this black hole starts to dominate the canonical ensemble and we have a universal result. And then we can also talk about microcanonical. So another thing is that microcanonical equals canonical should not be taken as granted. So because in large central charge CFT, they becomes very, very subtle. So for example, we can show that for 2-point correlators in heavy state, they approximately behave as thermal correlator only in this regime. Outside this regime, it is not guaranteed that this inequality will hold. So here the point is, as Euclidean time separation between these two operators is less than the length of the spatial circle, the microcanonical answer cannot see the finite spatial length. So we obtain a canonical answer for CFT on infinite line. So, and this behavior is also true if one do this analysis for endpoint correlator with different separation. And another technical remark is that the Beurling-Selberg optimizer can be also written down for a two variable problem. So one might want to do this analysis as a function of left and right moving conformal weights separately. But again, it turns out the optimal solution coming from the mass problem does not coincide with the optimality in the sense of CFT. So, so, so one needs to use the T invariance, and only then one can do a fixed spin analysis, and only then the two notion of optimality coincides. So either I have to do a fixed, I have to do an analysis which is only a function of delta, or I have to do an analysis using T invariance, project onto fixed spin, and then do a delta dependent analysis. Only in these two scenarios, the notion of optimality from the mass problem matches with the notion of optimality from the CFT problem. And finally, I would like to mention some open problems, as I briefly mentioned also before, that the optimal bounds are not central charge dependent. So these are the optimal bounds which uniformly applies for all central charge. So maybe one can try to like look at some particular CFT with some particular central charge and better these bounds, much like the bounds that has been recently obtained in context of modular bootstrap and sphere packing in the paper of Dalimil and other people. And then another hard problem is to defining proper notion of chaotic CFT so that one can see these finite universal features. A natural choice is to impose the twist gap, but it seems not enough. And then one can also hope to generalize these techniques for 4-point function in higher dimension or higher genus partition function, maybe with numerical assistance. Thank you.
Thank you so much for the great talk. Are there any questions? I do have one question. So when you mentioned large central charge CFTs,
Yeah.
so you to get rho of delta, the density of states, you truncated the interval over time from to some lambda, from minus infinity to infinity, from
Yeah.
some minus lambda to lambda.
Yeah.
Now, what is the order of limits that you're taking here? Are you taking C to be much larger than lambda? The C.
Oh, yeah, C is always, yeah, C is infinity, right? C goes to infinity, and whereas by lambda, you mean this cutoff, right?
Yeah, so I see. So
lambda is always order one number.
So all the recurrences have gone away, right?
Yeah, yeah.
I see. All right.
So you can think of it this following way, that what is the least possible recurrence time in a CFT? It is twice pi, right? When the spectrum is integer gapped.
For sure. Yeah.
So that's the best possible lambda you can choose. Lambda equals twice pi. So that's roughly the intuition.
I see. Thanks.
So you have to stop before recurrence happening.
Are there any other questions?
I have a naive questions about, I mean, maybe it's not for the analysis that you want to prove, but when you are doing a Fourier transform, and then you are chopping the integral with like a cutoff, like a, well, like you say, the function of the interval, but for a Fourier transform, it's better usually to put a cutoff like smooth, like a Gaussian or some Dirichlet function or something. If you suppose you're doing some numerical Fourier transform and you don't want to integrate to infinity, it's better to put a smooth cutoff.
What kind of cutoff are you exactly referring?
In you integrate t between minus lambda and lambda instead of minus to plus infinity, because you are putting a quasi-periodic function or something, and then you're doing Fourier transform.
Yeah.
But when you Fourier transform, if you are then you are inserting a theta, I mean a heaviside function from minus lambda to lambda.
Yeah. So I guess the whole, I guess my point was so when I am doing the Fourier transform, instead of this function theta, see.
Oh, it's the same. I don't know. There is another formula where you have z of beta plus it e to the minus beta plus it delta.
Yeah.
Yeah, there you are chopping between minus lambda and lambda. Is this same plot here, or?
Oh, I see. What? So the point is, I am not exactly okay. I guess I realize. So the point is, I am chopping the integral between minus lambda to plus lambda, plus I also have these smooth functions phi plus and phi minus, which comes as a regulator. So it's not like direct chopping with the heaviside function.
That's what because direct chopping will increase a lot of the higher frequencies. But
Yeah. So yeah, exactly. So it's not a like exact chopping. Like so, I guess. Let me see whether I wrote down this thing somewhere. So you can see this. Yeah, you can see here. So this is of this integral is of this form. So originally this integral goes from minus infinity to plus infinity, and I have this regulator. And then I choose this function in a way so that this integral gets cut off at minus lambda to plus lambda. But I still have this phi plus t, which is not the Heaviside function. Rather, this is some smooth thing. Yeah.
okay, well, thank you.
Yeah. Thanks.
Last question.
Yeah, I have a common question, maybe. So just a naive observation that these functions that you're getting out of this extremization procedure, like sines over polynomials, sines over sine over x, and so on.
Yeah.
There's a very similar result in a two-dimensional case. So if you take like a 2D CFT, and you try to like for the case of a free boson for C equals 1, and you try to find a functional in the sense of the bootstrap, you get essentially the product of two functions that look very similar to what you have. You essentially get sine of h over h bar, sine of h plus h bar over h plus h bar product, another sign that looks very similar. I wonder if this extremization procedure gives you a way of trying to generate analytic functionals for the modular bootstrap.
I see.
You know what I mean? So
Yeah, I see. Yeah, that might. Yeah, so Bauer and I was thinking about this a bit some time back. Yeah, but we did not have anything concrete in this line. But yeah. So this construction looks very similar in also other sense. For example, in this construction of Dalimil, Hartmann, and Rastelli, they have this construction where you have double zeros inside something, and then outside you have single zeros, and there are extremals. So there are tons of similarities. But
so you've thought about this, and like there was nothing obvious that popped out at you.
Yeah, and so the point, I think another point is to make so at least the extremal functions that appears in the sphere packing context, I believe that those are not band limited functions. But here all the functions that appear, they are band limited, and only for the case where you can relate the problem with a 1D bootstrap 1D sphere packing problem. Only then the extremal function. So okay, let me rephrase. So the extremal function that you can write down for 1D sphere packing, which is of course trivial, but still if you want to write down, then that extremal function precisely band limited, and then that extremal function is same as the function, same kind of functions that appearing in this problem. But if you go beyond 1D, then Henry Cohn has an argument which says that the functions that extremizes the sphere packing problem cannot be band limited.
Right. Well, the case I'm telling you is for the case of D equals 2 sphere packing, yet the extremal function is a sine x over x type function.
I see.
For the C equals 1, it's the same as the D equals 2 sphere packing problem.
Okay, then maybe in D equals 2 also there is some statement like that.
Yeah, maybe something special happens.
Yeah.
Okay, thanks.
Yeah, but I guess one would try to see whether, like, I don't know. So the point is one would try one can try to use these extremal functions and feed it in the modular bootstrap and see whether something comes out.
Maybe it's a good basis or something. It doesn't have to be exact. I'll be happy if it gives me some way of getting mix of analytic and numerics, you know.
Yeah. That could pretty well be the possibility. But yeah, we have not tried anything concrete in this line, like trying in the feeding it in the modular bootstrap.
Yes.
Okay, thank you so much. Thanks everyone. Thanks Sridip for the great talk. And yeah, we're gonna post this on YouTube.